Okay, y'all. So this is my third attempt of recording this video because I made a mistake and then Zoom did weird things. So let's hope this works out better. We are going to talk about what happens when all of our trig functions have even powers, when we have both sine and cosine to even powers. There are no odd powers hanging out in here. And this is different than what we did last class. So if we look at sine squared dx, last time we talked about the fact that we can't use our methods from before because as it is right now, we don't know how to antidifferentiate sine squared. We can't use a u substitution here. We could try rewriting this as 1 minus cosine squared, but that doesn't change anything. That's really just as bad as sine squared. So we need a different trig identity here. And that's where these two trig identities are to come into play. Those are not negative signs in front, those are just dashes. So here we're going to use the second of these two trig identities. Both of these are power lowering trig identities. They start out with a sine squared or a cosine squared, and they give us a cosine to the first power. And cosine to the first power is something we know how to anti-differentiate, so that's good. So in this case, I'm going to use the second one. I'll pull that 1/2 out front. I have 1 minus cosine 2x dx. And now I can just anti-differentiate. 1/2 x minus antiderivative of cosine 2x is going to be sine of 2x with a 1/2 out front from a u substitution. And if you can do that without writing out the steps of the u substitution, that's okay. If you need to write out the u substitution, you would be picking u to be 2x and going from there. Okay, so that first one's pretty easy. If we have both sine and cosine to even powers, we're going to use this technique, and these problems can get messier, which we'll see in just a minute. And so if I have both sine and cosine to even powers, I rewrite everything using these identities, and we'll see how that happens in a second. And then what we saw last time was this is if either sine or cosine is to an odd power, then we isolate a single sine or cosine, which will become our du, and then we do a u substitution after rewriting everything else. Okay, so let's look at this next one. This next one has both sine and cosine to an even power, so we're going to have to use our power lowering formulas, and we're going to have to rewrite everything. So sine squared is going to become 1/2 1 minus cosine 2x. Cosine to the fourth is the same thing as cosine squared times cosine squared. So we can rewrite that. We can use this identity twice. 1/2 times 1 plus cosine 2x times 1/2 times 1 plus cosine 2x. Okay, now we have a bunch of things multiplied together. So we're going to have to multiply this all out. 1/2 times 1/2 times 1/2 is 1/8. I'll pull that all the way out. If I multiply these two things together, if I FOIL that out, I'm just going to get 1 minus cosine squared of 2x, and you should double check and make sure that makes sense. And then I still have this piece left, 1 plus cosine 2x dx. Okay, now I'm just going to have to keep multiplying out. This is why these get messy when both sine and cosine are to higher powers and they're both even, is because there's a lot of multiplication that has to happen. Okay, so if I FOIL now, I'm going to have 1 plus cosine 2x minus cosine squared 2x minus cosine cubed 2x. And now we're just going to anti-differentiate. So I get 1/2 or 1/8, sorry, in big parentheses. 1 becomes x. Cosine 2x, you could do a u substitution where your u is 2x, and that's going to become 1/2 sine of 2x. And now things get interesting. So I have cosine to an even power, which means I'm going to have to use my power lowering formulas again. So this is going to become minus 1/2. I'm going to use this power lowering formula. And let's see what happens. So cosine squared of 2x. What I'm doing here is I'm replacing that x with a 2x. So I'm going to get 1/2 times 1 plus cosine. I'm going to have 2 times 2x. So this is going to give me cosine of 4x. So be careful if you have something inside of the cosine squared or inside of the sine squared that you have to replace this piece with whatever that expression was. Ask me in class if that doesn't make sense. So this is going to be 1 plus cosine 4x dx. Okay, and this last piece is cosine cubed. That's cosine to an odd power. So we're going to have to use the techniques from last class. So we can rewrite this as, let me write it up here. So we can write it as cosine squared times cosine. We rewrite that cosine squared as 1 minus sine squared x cosine x. Remember, we're doing this because this is an odd power. We're going to be able to do a u substitution here. So I have 1 minus sine squared x, oops, that's a cosine, cosine x dx. Okay, I'm gonna keep working on that red piece because I think it'll be easier just to finish that. So we do a u substitution here where u is sine x, so our du is cosine x dx. So we're gonna have minus the integral of 1 minus u squared du, which will become minus u plus 1/3 u cubed if I distribute that negative. So that's going to become minus my u is sine minus sine x plus 1/3 sine cubed x. Okay, so we're gonna that's gonna be our last piece. Let's work with this piece here. Its antiderivative is going to be minus 1/2 all times x. Antiderivative of cosine for x is 1/4 sine for x. Okay, and then we could just copy this down. So I have 1/8 times x plus 1/2 sine 2x minus all of that. And don't forget a plus c at the end. Okay, so you'll notice that this was really messy. This is why we're not going to do too many expressions where we have sine and cosine to very big even powers, because they get messier and messier. If this was sine to the 8th, cosine to the 10th, we would be here for a while doing these problems.